Hello everyone and welcome back. We are talking about related rates, and in the last video we looked at related rates with Pythagorean's theorem, and now we're going to look at related rates problems where similar triangles comes into play. And just recall, when going about these problems, you always want to typically draw a picture first and to understand the geometry at play. Okay, and I'm going to add a third hint as we go on, but you'll see that through the examples here. So here are two examples similar to what you'll see in your work to give you a better idea. So example one, Sam is walking away from a street light 10 feet tall at a rate of 2 feet per second. If Sam is 6 feet tall, how fast is the shadow moving when she is 10 feet away from the street light? And then later, what if she's 20 feet away? What is that? So again, so visually, let's see what's happening. So we have a street light. So that's your light. And we know the light's 10 feet tall. And then I'm going to draw the triangle first to make sure the picture is a little bit more accurate. And then we have Sam, who is 6 feet tall. And if we denote the distance between, well, there, we'll just mark this. So we have that. And then this right here will be the shadow of the light. So you can imagine a light coming, the shadow's there. Now, understanding this problem, what do we have here is notice that we have a triangle within a triangle. And then what we also can see is by this angle that they share, that we know that these triangles are similar. So by angle similarity, that'll allow us to do some work in a second. Now, how else might we label this photo? So we don't know the distance between them, which later we're going to say that's 10, but that's okay for now. And we know that she is walking away from the streetlight, so then we know that dx dt relative to time is equal to 2 as she moves away from the streetlight. And then the shadow, I don't want to use it. I'll use s, that's okay. I was going to say, I did a problem earlier where it was a 5, and I don't like using 5s and s's. I get confused with my own work. So we'll denote the shadow length as s. And then what are we trying to solve here is how fast is the shadow moving? So basically what we're trying to do is figure out what's ds dt. So how fast is the shadow moving relative to time when she is 10 feet away? So when x is equal to 10 feet. Okay, so that's what we're trying to solve in this problem. So by angle similarity, since these triangles are similar, what can we say then? Is then we can say that 6 over 10 will we'll have a similar scale factor as s over x plus s, that length. Okay. And then solving here, and you could have also done this by 6 over s is related to 10 over x plus s, just different ways of writing the proportion. In the end, it all works out the same way. So you'd get 6x plus 6s. Combining the s's, we would have minus that. So you'd have 4s equals 6s. And then to understand the rates of this problem is we want to understand how is all of this changing relative to time. So we're going to take the derivative in respect to time. What we'd have here is 4 times the derivative of s with respect to time. So we don't know, so implicitly we just write ds dt. It's equal to the derivative of 6x would be 6, and then the derivative of x is going to be dx dt. Okay. So what we see here is that ds dt, which is what we're solving for, the rate at which the shadow is moving relative to time, is going to equal 6. And then dx dt we know is 2, so we can plug in a 2 there, divided by 4, which is going to equal 12 over 4, which is 3. And there you have it. So the shadow is moving at a rate of 3 feet per second. If we check the units there too, 6 was feet, so you have feet times 2, which is feet per second. So that would be giving us the feet squared per second. Where am I messing up? Why is it feet squared per second? And then you divide by 4. And what's the 4 represent here again? 4 was 4s, the length of the shadow. Why is the units not matching up? Let me think for a second. Oh, well, the 6 wasn't actually feet. I see. I got confused. I was correlating the 6 with the height of the person here, but 6 ended up being the coefficient. So it doesn't. That's not the x that we plugged in. I guess it is. That's technically the height of the person. So I guess that would have been feet. The 4 would have been feet, in which those feet would have canceled and would have been left with feet per second. So that works for us. Sorry, I got a little caught up in the units because I was like, I'm pretty sure it's feet per second. Let me check the units. And yeah, the 4, if we combined the 10 and the s, was still in feet. The 6 was in feet. And then the feet per second, which that leaves us with our proper units. So that's great. So when she's 10 meters away, she was 3 feet per second. Now you might be thinking, wait a second, Mr. Hein, we didn't use the 10, right? We didn't use the fact that x equals 10. So what if you would have plugged 10 in? So let's return back to this orange palm. What if we wrote 6 over 10 equals s over, and then write x plus s? Same thing. Well, I guess instead of x, what if we would have wrote 10 there? Since we know that x was 10 feet away. What if? Okay. So then what you would have had is 60 plus 6s equals 10s. 60 equals 4s. And notice when you take the derivative of this with respect to time, you're going to get 0 equals 4 ds dt. Well, that's strange, because if you solve for ds dt, then you would imply that the rate at which the shadow is moving in relation to time is equal to 0. And that doesn't make sense, because the shadow will be moving. So why did that happen? And this is a mistake. And that mistake is, don't plug in before you implicitly differentiate. Okay. You have to differentiate first before you plug in any numbers. And that's the mistake I wanted you to see in this problem. So I would have added that to my third hint up here. Draw a picture, understand the geometry. In 3, implicit differentiation to look at the rates before plugging anything in. Before, substituting values. There's a little bit more of a math term there. There you go. Now, I figured out how fast she was going when she was 10 feet away. Now, would it matter 20 feet away? Now, notice to 20 feet away, it'll still be the same answer. The same answer is there. It's still going to be 3 feet per second, because the fact here is we never even used the 10. The dsdt does not rely on what x is. It only is in relation to the rate at which she's moving away and the length of the light and herself. X was never involved in knowing this, which is very interesting. Okay, good. Let's look at example 2. Something a little bit different. A tank of water in the shape of a cone is leaking water at a rate of 2 cubic feet per hour. The base radius of the tank is 5 feet and the height of the water is 14 feet. At what rate is the depth of water changing when the depth is 6 feet? So don't get caught up in the words, just take it slow. Draw a picture. So we have a cone shape. It looks something like this. And we know that the radius is 5 feet. We know that the height is 14 feet. And it's filled with water, so imagine that all of this has some sort of liquid in it. Or I guess water is telling us. And it's leaking water at 2 cubic feet per hour. So then we know that dV dt, the volume in relation to time, is equal to -2 cubic feet per hour. So we know that. Okay. At what rate is the depth of water changing? So depth of water, so I'm going to call this H. I guess I should call it D, but I'm going to call it H. H will represent the depth of water here. So we want to know at what rate, so we want to know what's dH dt changing when the depth is 6 feet, when h equals 6. And that's what we're trying to solve here. Okay. Now, what's the geometry at play here? Now, in this problem with a cone, it actually, what we can end up creating is a right triangle. So if I pull that out, what you can see here is that we actually have a right triangle where this is 5, and then there's some water in it down here, and that's also a right triangle. And we know the entire length here is 14. Okay. Well, if we label this as the height of the water, which we don't know, h, and then this is the radius of the water, which we don't know, what can we say is by angle-angle similarity, we might say that r over 5 has to be related to h over 14. Okay. Now, big picture here, why am I even doing this? What if we just, we're talking about at what rate is the depth of water tank changing? Well, we're talking about volume, so it's like, dang, this time, why don't we just go straight to volume? Well, we could have, so let's do that. The volume of a cone is 1/3 pi r squared h, because it's the volume of a cylinder, and 3 cones make a cylinder, is where that comes from. And notice, if we take the derivative of this with respect to time, what you're going to end up getting is dv dt is equal to, I'm going to combine the pi thirds because that's just a constant, and you have 2r dr dt. Well, you end up having to do the product rule, so it's not even this. I almost missed that. Where it's going to be the first times the derivative of the second plus the second times the derivative of the first. And notice what we get is that the volume depends on knowing the rate at which the depth of the water is changing. You need to know the radius of the water. You need to know the height of which the water is at. You need to know the rate at which the rate is changing. So basically, there's a lot you need to know here. But the information we have, we only knew dv dt, so we could plug that in. We knew h. Careful, this radius is the radius of the tank, not of the liquid itself. So we don't actually know r here. And we're trying to find dh dt, but we don't even know dr dt. So you can see here there's a lot missing. So what I'm trying to do here is basically understand h or r in terms of each other. Now I'm actually going to try to understand what r is in terms of h, so I can write all of this function with just h, because that's what we do know, is we want to know the height of 6. So we're going to head there. We're going to get back to this so you understand why I'm doing all this. So what you get here, if we go back to this similar problem, is 5h equals 14r. And I'm going to write it as the radius is equal to 5/14 h. And again, I want it in terms of h, since we want to know how's the depth. I know height is a bad word, h for depth, but we want to know how is that changing when the depth is 6. So we want to keep it in terms of h. So now if we return to our volume equation, let's return back to it. Pi thirds r squared h. Well, before I even differentiate and have to deal with the product rule, I'm going to substitute r is related to the height of the water by similar triangles as 5/14 h squared, and then times h. And then what you end up getting there, I might need another piece of paper so I don't get too tight on my work, is we're going to end up getting the volume is equal to, that would make 25, so we're going to have 25 pi over, I don't know what 14 times 14 is. Let me do that. 14 times 14 times 3 over 588. So 25 pi over 588 h to the third, because the h here and the h would make h to the third. And now we can take the derivative of this with respect to time and say, hey, the volume of the water changing is going to equal, now all of that's just a number, so we don't have to worry about that when differentiating. Pull that out in front. And the derivative of h to the third is going to be 3h squared dh dt. And notice again in this problem, we're trying to figure out what dh dt is when h equals 6. So we know h is 6, and then we also know that the volume was changing at a rate of -2. So if we plug all that in, we would have -2 equals, that's going to be 75 pi over 588 times 6 squared times dh dt. And now we just solve for dh dt, and what we'll get here is -2. I'm just going to divide by all that and just use my calculator, divided by 75 pi over 588 times 6 squared. And what's dH/dt? Okay. So here we go. It's going to be negative 2 divided by 75 pi divided by 588 times 6 squared. And I know that that's okay because multiplication division order doesn't necessarily matter. What I get here is dH/dt is equal to negative 0.139. Height is feet, so feet per hour. And that makes sense in this problem in the sense that if you're leaking water, right, if you're losing water at 2 feet per hour, then the height should be going down. So it's good that the rate is negative, showing that. So there's 2 examples. I hope you kind of follow along with the thought process of them. Definitely, you need to try it yourself. All right, don't be too quick at looking at the answer key to see how far you can get without it. If you have any questions, feel free to stop by office hours or ask. All right, bye-bye.